Hello.
Hello.
Shall I start? Hello.
Yes, sir, you can start.
Okay. Can you see my screen?
Yes, sir, we can see.
Okay. So let's start. Good evening, everyone.
Good evening, sir.
Okay. So you are enrolled for mathematical methods in Physics 1. The course instructor is Professor Aditya Sharma. So I am Dhiren. So I will solve the previous year assignment, which will help you to submit the assignments later on. So let's start with problem number 1. So my voice is clear.
Yes,
Yes,
sir,
sir,
also.
it's clear.
Okay. So the problem number 1 is using vectors, check which of the following statement is true. So the four options are given. The option A is the diagonals of a parallelogram bisect each other. The line segment joining the midpoint of two sides of any triangle is parallel to the third side and half its length. The option says in a parallelogram, the two lines from one corner to the midpoints of the two opposite sides trisect the diagonal they cross. And the fourth one is the sum of the squares of the diagonals of a parallelogram is equal to twice the sum of the squares of two adjacent sides of the parallelogram. So the answer is I have given here, but I will explain how. I will explain one of the four among the four option. I will explain one, and later you can also in the same way you can find the answer for all other options. So I'll start with option number C. Uh, let's start. So, what is given in option number C? In a parallelogram, the uh, two lines from one corner to the midpoint of two opposite sides trisect the diagonal they cross. Let's draw a parallelogram. So we can name the parallelogram A, B, C, D. Then we can draw the two diagonals. And the question is the statement is, in a parallelogram, two lines from one corner to the midpoints of two opposite sides. So we can draw two lines here to the midpoint of the opposite sides. Sorry. Yeah. So you can draw the parallelogram. So then the diagonals are these. The name of the diagonals are A, B, C, D, and we can draw two lines to the mid of the diagonal here, and we can name it as F and E. This one is H and this one is G. So the statement is, in a parallelogram, the two lines from one corner to the midpoints of two opposite sides trisect the diagonal they cross. That means these two lines AF and AE trisects the diagonal they cross. That means they trisect the diagonal B and D. So that means, see, if we write that BG is 1 by 3 BD. That means BG is this one, BG is 1/3 of BD. So let's prove. Let AB is equal to DC is X. So this AB is equal to DC because this is a parallelogram. So we can suppose let it say X vector, and AD is equal to BC equal to Y. So as we know that any vector can be written as the linear combinations of X and Y. So here AE vector is equal to AB vector plus BE vector. So AE is equal to AB vector plus BE vector. See, that means AB plus this BE vector is can be written as half of BC vector because this is the midpoint. So this one is BC vector by 2 is equal to X plus Y by 2. AB is X, we have assumed, and BC is Y, so that is X plus Y by 2. And here AB plus BD is equal to AD, and AB plus BD equal to AD. So we can get here BD vector is equal to AD minus AB vector. So that is equal to AD is, we have mentioned Y vector minus x vector. So next what we can do, that from this figure we know that just this is a parallelogram, so bz vector is parallel to bd vector, because bg vector, this one, is along the direction of bd vector, that means they are parallel. So that leads to bz vector is some linear combinations or some multiplication factor with bd vector, because this is the total vector and this is a small portion of this vector, so this can be written as some parameter into bd. Let this parameter is alpha, and we can write that alpha into y minus x, because we have mentioned that bd vector is y minus x, so that is this. So again, AG vector is parallel to AE vector. So AG vector, this one, is parallel to AE vector because this is in the same direction, and we can also write that AG vector is some parameter multiplied with AE vector. So that one is beta into this a is mentioned as x vector plus y 2 vector. So now we can say that ag vector is equal to, we can say that ag vector is equal to ab vector plus bg vector. So we can write ag vector is equal to ab vector plus bg vector. So that means beta ag vector is mentioned as beta x plus y 2, and is equal to ab vector is x plus alpha into y minus x. So we can bring this into this side, so it will be alpha plus beta minus 1 x vector plus beta by 2 minus alpha y vector is equal to 0. As we know that this x and y cannot be 0, so alpha plus beta minus 1 is equal to 0, and beta by 2 minus alpha is equal to 0. So from here we can get alpha plus beta equal to 1, and here we can get alpha is equal to, here we can get that beta is equal to, hello, are you there? Beta is equal to 2 alpha. So here we can get beta equal to 2 alpha, so you can substitute here alpha plus beta means 2 alpha equal to 1, so alpha is equal to 1 by 3. So above we have mentioned that bg is equal to 1 by 3 beta, we have assumed. So here we get also alpha is 1 by 3, that means the statement is true. The statement C is true. So you can check all other statement also, like simple vector addition, using simple vector additions. Hello, hello,
Yes, sir. Yes, sir. Audible, sir.
you got?
You're audible, sir.
Okay, okay. So coming to the next problem, problem number 2. So consider the ordinary vectors in 3 dimensions, which is ax ex hat plus by ey hat plus cz ez hat with a complex components. Which of the following statement is true? So here all options are given. So we will check which option will be true. So I will check first two options. So rest of the options you can choose or check accordingly. So coming to the next, uh, here it's mentioned that the vector, the subset of all vectors with az equal to 0. The first option is the subset of all vectors with az equal to 0 constitute a vector space. So we need to check whether it's actually true or not. So let's define a vector space. Let's define vector v1 is a subset of all vectors with az equal to 0. Then that this means v1 is ax ex cap plus ay ey cap plus az. In the place of az we will put 0 e z cap for all ax ay belongs to R. So for checking whether this subset is forming a vector space or not, we have to check three properties. One is closure property. Second one is if there exists an identity element. Third one is inverse element. Let's check with first one, closure property. Let a and b are two vectors belongs to a vector space v1. That means a is ax e cap plus ay ey cap plus 0 into ez, because it's mentioned that az equal to 0. And let b vector is bx ex cap plus by ey cap plus 0 into ez cap. So what do we mean by closure property? That means we can write a vector c with linear combinations of these two vectors. So c can be written as a alpha a vector plus beta b vector. So here alpha into a vector is ax ex cap plus ay ey cap plus 0 into ez cap plus beta into bx ex cap plus by ey cap plus bz ez cap. Here bz is equal to 0. So let's check it is satisfying the closure property or not. So here mm, this alpha ax plus beta bx, if we expand we can get this term, and alpha ay plus beta by ey cap plus 0 ez cap, because all the z quantities are 0. So here this term can be written as cx as a shorthand notation. This one is cy and cz is 0. So here it will be like ex cap plus cy ey cap plus 0 ez cap. So our statement was that the subset of all vectors with a0 constitute a vector space. So this vector space satisfy the closure property, because this the new vector we got is also z component 0. So the closure property is satisfied. So next we have to check if it's satisfying the identity property. So next, for identity element, so there is a null vector which is also belongs to the same vector space plus 0 ey plus 0 ez. So it's an element of v1, such that if we add any vector to the null vector, it will be the same vector, that is a, for all a belongs to the vector space v1. Hence here the identity element also exists in the vector space. Similarly, we have to check for inverse. Inverse for every vector a, ax ex cap plus ay ey cap plus az ez cap. Here az is 0, so belongs to vector space v1. Let's test if there exists an identity. So define in a prime vector, so that is minus ax ex cap minus ay ey cap plus 0 ez cap, which also belongs to b1. So if we add a plus a prime, that means we will get the null vector, because inverse, if we are adding a vector with its inverse, then we will get 0 null vector. So this null vector is also exist in v1. Here all three properties are satisfied, so the vector space b is equal to ax ex cap plus ay ey cap plus 0 ez, for ax ay belongs to R is a vector space. Similarly, you can check option B also. Let's see what option B is. So option B is the set of all vectors with az equal to 1 constitutes a vector space. So let's test whether it's a will be a vector space or not. I'll briefly explain. So in the space for the next So here it will not satisfy this 0. Here it's az is equal to 1. For the second option it's given az equal to 1. If we write the vector like a1 is equal to ax ex plus ay ey plus az ez, here az is 1 for option B. Similarly for b1 is bx ex plus by ey plus bz ez, bz is also 1. So let's test the closure property, that is c1 is, we can write alpha 1 plus a1 plus beta 1 b1. Similar fashion just I explained in the before. So here we will get that alpha 1 ax plus beta 1 bx ex plus a alpha 1 ay plus beta 1 by into ey cap plus alpha plus beta ez. And for the satisfy the closure property, it should equal to cx ex plus cy ey plus 1 ez. But we get alpha 1 ax plus beta 1. If we consider it as cx, this one is cy, this one is cz, but here we got cz which is not equal to 1. Here in the previous case we get cz is equal to 0, as we mentioned that all the vectors with az equal to 0 will constitute a vector space. Here we have previously had that a z or c z is equal to 1, but we got alpha plus beta, we got the different one. So this closure property is not satisfied. So hence if one of the three properties is not satisfying, then it will not form a vector space. So coming to the next problem, problem number 3. Which of the following collection of polynomials constitute a vector space? So the options are the collection of all polynomials with complex coefficients of degrees less than n in x, the collection of all the even polynomials with complex coefficients of degree less than n in x, the collection of all the polynomials with complex coefficients of degree less than n in x which takes the value 1 at x equal to 0, the collection of all the polynomials with complex coefficients of degrees less than n in x which takes the value 0 at x equal to 1. So here I will explain the option number 1, and the other options you can check in the similar way. So to satisfy or to be a part of vector space, as I mentioned that there needs to be satisfied three properties. One is closure property, one is identity, and another one is inverse. So we can start with by checking closure property. So given that the collection of all the polynomials of degrees less than n in x, so let the B1 is collection of polynomials of degree less than n in X. That means B1 is f of X is equal to A0 plus A1X plus A2X square plus A n minus 1 x to the power n minus 1, where ai belongs to complex number set. For I equal to 1 to n minus 1. So this defines closure property. We need to check first the closure property. Let f of x g of x belongs to v1. So that means f of x can be written as I equal to 1 n minus 1, as it mentioned that the degree is less than n, so it will run up to 1 to n minus 1 ai x to the power I, and gx is summation over I equal to 0 to n minus 1 bi x to the power I. So as you know that any vector of a vector space can be written as the linear combinations. Here also we can write h of x is equal to alpha f of x plus beta g of x, where alpha and beta belongs to complex number set. So here alpha we can expand fx and gx. So I equal to 0 to n minus 1 alpha ai plus beta bi into xi. If we expand these two terms and then taking common alpha a plus beta bi, we'll get this. So let's say this one is ci. We can h of x is equal to I equal to 0 n minus 1 ci xi. So this closure property is satisfied. So this hx is also an element of B1. So coming to the next identity element. So identity elements means we can denote as ox, which is also 0 for all x belongs to R, where R is a real number set, is n element of B1, such that f of x plus ox is equal to ox plus f of x is equal to f of x for all f of x belongs to B1. So we see that these identity elements also exist. So identity property is also satisfied. Then we have to check for inverse. So for every f of x I equal to 0 to n minus 1 ai x AIXI belongs to V1. There exists another vector which is also known as inverse, is equal to summation over I equal to 0 n minus 1 minus AIXI, which also belongs to the same vector space V1, such that f of x plus f of prime x is equal to the null vector. So here also we can see that inverse property is also satisfied. So this, the collection of all polynomials with complex coefficient of degrees less than n in X constitute a vector space. Hello. Hello. Coming to the problem number 4, let A be a set of m cross n matrices with real elements, and let B be the set of m cross n matrices with complex elements. We wish to think of the elements of these sets as vectors. Let us take the operation of addition of matrices, like we are familiar, to be the addition of vectors. Also, let us restrict the scalars with which we multiplied the vectors to be real numbers. Which of the following statement is true? So options are: only A is a vector space, only B is a vector space, neither A nor B is a vector space, both A and B are vector space. So we'll check for A, then similarly we can check for B whether it's a vector space or not. So coming to the solution, let A be a m cross n matrices with real elements. Then we need to check three properties like closure, identity, and inverse property. So for closure property, let x comma y belongs to a vector space A. Now any vector can be written as a linear combination of two generic vectors. So let J is another vector which can be written as linear combinations of alpha x plus beta y. So here alpha and beta belongs to real. So this alpha x and beta y, so hence this also satisfied that z also belongs, z is belongs to the vector space A. That means the closure property is satisfied. So to check the identity property, the matrix, let the matrix O with all its element as 0 is an element of A. It's given previously that A be a set of m cross n matrices with real elements. So 0 matrix is also an element of the total matrix A. So we can write that any vector plus null is equal to x. That means there exists an identity element for all x belongs to A. So this satisfied the identity property. So we can check for the inverse also. So we can check for the inverse also. Let's x belongs to A. There exists an inverse matrix x prime which is belongs to A. Let the element of x prime is ij, x prime ij is equal to minus of elements of xij for all I, because it's given m cross n matrix, so I runs from 1 to m and j runs from j1 to n, such that x plus x prime is equal to x prime plus x is equal to 0. This satisfied the inverse property that the matrix plus its inverse gives the null matrix, and then it's satisfying all the three properties. So A is a vector space. So similarly you can check for the B also, and it will be for the vector space also. So coming to the question number 5. So the given a system of equations, this is the equations. So let M be the matrix of coefficients and A be the augmented matrix. Which of the following statement is true? So this given this linear set of linear equations which coefficients are, let's say x has a coefficient y and y has a coefficient 1 and z has a coefficient 2, and in the second equation it's also given 1 minus 1 1, and in the third equation it's 2 4 and 5. So we can form a matrix by using these linear equations. So we have to check whether what is the matrix of what is the rank of the matrix of coefficients and the augmented matrix A. So first we need to check what is the coefficient matrix. So here we can write this set of linear equations in the form of m x equal to c. Here m is the coefficient matrix and x is a column vector and c is also a column vector. So here we can write the coefficient matrix from the equations as m equal to 1 1 2 1 minus 1 1 2 4 5, and the x is, let's say, x y z, and c is given 1 2 4. So to solve these linear equations we use the row reduced form. So in this technique we just need to find what is the coefficient matrix and what is the augmented matrix, then we can reduce that augmented matrix with row operations, then we will get the row reduced from, and then we can find the rank of the matrix M and A. So let's do how to do this, how to get the rank of matrix A and M. So here we get the coefficient matrix M, so then the corresponding matrix, augmented matrix A is equal to M C. This is 1 1 2 1 minus 1 1 2 4 5, and the augmented matrix is C, means we have to write 1 2 1. So after that we have to do the row operation, so that we will get a upper triangular matrix. That means this the lower elements will be 0. That means we will get the upper triangular matrix. Let's do the row operations. Like first row operation, so let's row operation means we need to change the row with the multiplicative factor with let's do r2 changes r2 minus r1. So we have this is the r2 row, we can change it at r2 minus r1, so that will be 1 1 2, then this one is r2 minus r1, so r2 is here 1, that will be 0, then this one is minus 2, sorry, minus 1, and r2 replace with r2 minus r1, r2 means minus 1 minus 1, that is minus 2, then this one is 1 minus 2, that is minus 1, and 2 4 5, and this will be 1, r2 changes to r2 minus r1, r2 here is 2, and this one is 1 and minus 1. After that again we can do the row reduction, and this will be r3 changes to r3 minus 2 r1. So again the A matrix will be 1 1 2 0 minus 2 minus 1 0 2 1, then this will be 1 1 minus 1. Again we can also change row is equal to row operation, r3 is changes to r3 plus r1, so A is 1 1 2 0 minus 2 minus 1, then 0 0 0, that one is 1 1 0, So here we got the lower triangular form. So here the C is the value of x and y and z we got 1 1 0. So here we can get the rank of the coefficient matrix and the augmented matrix. The rank of the coefficient matrix is here is 2, because there is the rank means the non-zero rows of a matrix. Coefficient matrix is 1, this 3 by 3 cross matrix, and the rank, there is 2 non-zero rows, so the rank is 2. And for the rank of the augmented matrix also, there is total, this in this matrix there is 2 non-zero row, so the rank of augmented matrix is also 2. Similarly, in other systems of linear equations, you can do the same procedure and get the rank of the matrix and augmented matrix. And basically this procedure is to solve the systems of linear equations, and you can easily get the solution to this set of linear equations by using this row reduced form. So coming to the next problem, which of the following statement is true? So the statements are given as a set of mutually orthogonal vectors may or may not be linear independent, and a linearly independent set of vectors need not be mutually orthogonal. A second one is a set of mutually orthogonal vectors is always linearly independent, and a linearly independent set of vectors must be mutually orthogonal. So a set of mutually, the third option is a set of mutually orthogonal vectors is always linearly independent, but a linearly independent set of vectors need not be mutually orthogonal. So the fourth one is a set of mutually orthogonal vectors may or may not be linearly independent, but a linearly dependent set of vectors must be mutually orthogonal. First, we need to know what do we mean by linear dependent or independent. Then we can check whether the which of the statements is correct or not. So here so what do you mean by linearly dependent or independent? So consider n vectors. So we can write in Dirac notation as gate 2 and the n vectors. If they are, let's say, linear independent, if they are linear independent, they will satisfy the relation that summation over I equal to 1 to n ai I is equal to 0. This implies that all the ai's are 0 for I equal to 1 to n, and if this is not satisfied, then they are not linearly independent, or they are linear dependent. So coming to the question number 6, which of the following statements is true? So I'll check for a set of mutually orthogonal vectors is always linearly independent, but linearly dependent set of vectors need not be mutually orthogonal. So if two vectors a1 and a2 are linearly independent, then alpha 1 linear combination, we can write it this form: alpha 1 a1 plus a2 alpha 2 a2 is equal to 0. As we know that they are linearly independent, so a1 and a2 are not 0, so alpha 1 is equal to alpha 2 is equal to 0. So here the two linearly independent vectors need not to be orthogonal. So we can check for the next possible: if two vectors a1 and a2 are orthogonal, that means their inner product a1 a2 should be 0. So if we check this condition, let's start with let a1 a2 an be n mutually orthogonal vectors. That means mutually orthogonal vector, that means ai az is equal to delta ij. That means 1 if I is equal to j, 0 if I is not equal to j. So let's take the inner product with am, where am is 1 to n. We get alpha 1 am a1 plus alpha 2 am a2 plus alpha n am an. That means they are mutually orthogonal, that will lead to a0. From here we can get here we can get am is equal to 0 for all n 1 to n. So from here we can get that a set of mutually orthogonal vectors is always linearly independent. That means the option C is correct. So next is, suppose we consider the space of two-dimensional vectors in which both the components are real, can be defined in the inner product of two vectors A, which has a component ax, ay, and B vector has components bx, by, as the dot product of A dot B is ax bx plus 1 by 2 ay by. So the question is, can you define the inner product two vector in like this? So would this be a legitimate scalar product? If yes, how does the Cauchy-Squarce inequality play out here? So we'll check the conditions if this is a legitimate scalar product, or how does the Cauchy-Squarce inequality play out here. As we know that the Cauchy-Squarce this will check that this be a legitimate scalar product or not, and also we will get the relation how the Cauchy-Squarce inequality play out here. So coming to the Cauchy-Squarce inequality, so this inequality is A if there are two vectors A comma B. So the inequality is like A dot B dot B cos square theta is less than or equal to A dot A or B dot B. So here the Cauchy-Squarce inequalities has the form like this. So again we will check the conditions that given that A dot B is equal to ax bx plus up into ay by, this is given. So due to the properties of dot product, so A dot B is equal to B dot A. So if A dot B is given, so B dot A will be bx ax plus 1 by 2 by ay, that is equal to A dot B. So here B dot A is equal to A dot B. So similarly for the another property, linearity property, so let C is defined as Cx and Cy, just as before mentioned that A is Ax Ay. So we can write that C dot alpha A plus beta B is equal to Cx alpha ax plus beta bx plus 1 by 2 cy alpha ay plus beta by. So here alpha, let's see, we can take out and can be written as cx ax plus, here also alpha is there, so we can get 1 plus 1 by 2 cy ay. Again we will get plus beta cx bx plus 1 by 2 cy by. So we can write this as alpha into c dot a plus beta into c dot b. It also satisfied the properties of a scalar product. So the another property of scalar product is the positivity property. That is a dot a is equal to ax square plus 1 by 2 ay square is always greater than or equal to 0, and is equal to 0 when the a is a null vector. So all these three properties satisfy the scalar product properties, and so it will be a legitimate scalar product. So next one is we have to check how the Cauchy-Squarce inequality is modified if we define the scalar product like this. So from the Cauchy-Squarce inequality we have a dot a is b dot b is greater than equal to a dot b and b dot a. As I mentioned previously, the Cauchy-Squarce inequality, there is a cos square theta factor. This cos square theta factor comes when we dot product with a vector. So here there was yes. So and the cos square theta value is always less than or equal to 1. So this Cauchy-Squarce inequality will reduce to this form. So before we have mentioned that the form of the dot product is a x square plus 1 by 2 ay square, and this dot product will give bx square plus 1 by 2 by square, which is greater than or equal to ax bx plus 1 by 2 ay by square. This square factor we can write a dot b is equal to b dot a. So we can expand in the above form like a dot a is equal to ax square plus ay square. Similarly, a dot b is equal to ax bx plus half ay by, and this one is also bx ax plus half ay by, and both are same, so we have squared this term. So if we expand this term, we will get ax square plus by square minus 2x bx ay by, and the terms we can replace into left side, that will be greater than or equal to 0. So this is equal to ax bx minus ay by, sorry, ax by and ay bx square is greater than 0. So the Cauchy-Squarez inequality is modified as this. So the option so the option so the option B is correct. So coming to the next problem, which of the following statement is true? So the options are: if two vectors are multiples of each other, the Cauchy-Squarez inequality for them becomes an equality, and the Cauchy-Squarez inequality becomes an equality only for two vectors that are multiples of each other. And the third statement is: for certain choices of inner product, it may be impossible to find vectors for which the Cauchy-Squarez inequality is an inequality. And for the option D, consider the vector space of complex numbers for which the scalar product is defined as Z1 inner product with Z2 is equal to Z1 star Z2. Here the Cauchy-Squarez inequality is always an equality since any two such vectors are multiples of each other. So we need to check which statements are true. So the solutions: let Z1 and Z2 be the two vectors, and it's given that given that given that two vectors are multiple of each other. That means this one is Z1 vector is some parameter multiplied with Z2 vector. Then we can write that the dual vector Z1 is equal to alpha star into Z2 vector. So now the Cauchy-Squarez inequality becomes Z1 Z2 inner product with Z1 is equal to 1 by alpha Z1 Z2 Z1 alpha Z2 Z2. That one is Z1 Z1 Z2 z2. Hence the CS inequality becomes an equality if and only if the two vectors are multiples of each other. So next, if we consider the vector space of complex numbers defined on a complex field, any two vectors z1 and z2 are multiples of each other, that means z2 is equal to alpha z1, where alpha belongs to the complex number set. So the CS inequality is always in equality. So here, from the above statements, option A, B and D are true. So the next problem is find the rank of the following matrix. So previously we explained from the systems of linear equation we can get the coefficient matrix, but here a matrix is given, so how to get the rank of this matrix? So there are four options given. Option A is 4, option B is 3, option C is 2 and option D is 1. To get the rank of this matrix, so we can use the row reduced techniques, and given the matrix is 1 2 2 4 3 1 4 5 1 minus 3 0 minus 3 5 0 6 6, as I mentioned previously, we need to do the row operations. So here I'll explain how to, which row operations we can get the row reduced form of this matrix, then we can find the rank of the matrix. So there are certain row operations I am writing directly, so you can check it and you can get the row reduced form. The operations are, first we need to do the R2 changes to step 1, R2 changes to R2 minus 3R1. So in the place of R2 you can replace this row matrix with R2 minus 3R1. Then you will get R, then you can do R3 changes to R3 minus R1. So R3 you can replace with R3 minus R1. Again in the third step we can do R4 changes to R4 minus 5 R1. So R4 changes to minus 5 R1. So our primary goal is to get a upper triangular matrix. So after these three operations we can get the matrix A in the form 1 0 0 0 2 minus 5 minus 5 minus 10 2 minus 2 minus 2 minus 4 4 minus 7 minus 7 minus 14. So again we can do the row operations. Step 4, R3 can change to R3 minus R1. Again in step 5, R4 changes to R4 minus 2R1. So after this operation we will get A as 1 2 2 4 0 minus 5 minus 2 minus 7 0 0 0 0 0 0 0 0. So as you know that from the row reduced form, so the number of non-zero rows is the rank of the matrix. Here there is 2 non-zero rows, so the rank of matrix is 2. So option C is correct. Similarly, in any matrix you can find the row reduced form and can get the rank of the matrix. So coming to the next problem and the last problem, let given is V1 with a space consisting of 2 cross 2 matrices with a complex entries, and the complex number forming the scalar field, let V2 be the space consisting of 2 cross 2 matrices with complex entries and the real number forming the scalar field. Which of the following statement is true? So the option A is both V1 and V2 are the vector space, and option B is only V1 is a vector space, and option C is only V2 is a vector space, and option D is neither V1 or nor V2 is a vector space. So as we know, to check the vector space we need to check whether three conditions are satisfied or not. So the first condition is closure property. So given that B1 is a vector space, so B1 can be written as 2 cross 2 matrix, because here it's given B1 with a space consisting of 2 cross 2 matrices with complex entries. So here A is a 2 cross 2 matrix with complex entries. That means the elements of this A matrix Aij belongs to a complex number set. For all I can be 1, 2, and J is also 1, 2, because it's a 2 cross 2 matrix. So this space is space defined on the scalar field F is equal to C, complex number. So we need to check whether this is satisfying the closure property, identity property, or inverse is exist. So let's closure property. So let A B belongs to B1, then as you know that any vector can be written as linear combination, so here C can be written as, here the matrix is the element of a vector space, so here C can be written as linear combinations of alpha A and beta B, where alpha and beta are complex quantity. So C has the elements, we can write it as Cij, is a element of A is Aij plus beta Bij. So this Cij belongs to the complex number set, which satisfied that C is the vector space B1. Hence the set B1 satisfies the closure property. Next we have to check the identity, whether there exists an identity element inside the set. So let 2 cross 2 matrix O defined as Oij is equal to 0, because identity in the null matrix there is all the elements are 0 for all I is equal to 1, 2, and J is equal to 1 to 2. So this is an element of B1, because we previously we have mentioned that there is mentioned that B1 be the space consisting of 2 cross 2 matrices with complex entries. So we can write A plus null matrix plus equal to 0 plus A, sorry, null matrix plus A equal to A for all A belongs to B1, and hence the identity element exists in B1. So the third property we need to check whether there exists an inverse element or not. For every A belongs to B1, there exists A prime belongs to B1, defined as a prime iz equal to minus of a iz. So for all I runs from 1 to 2 and j also runs from 1 to 2. So such that a plus a prime is equal to a prime plus a will give the null matrix. Hence here every element of v1 has a corresponding
Sorry, I don't understand.
inverse element in v1. So hence the set v1 is a vector space. Similarly, it can be proved that v2 is also a vector space. So both v1 and v2 are the vector space. So the option A is correct. So that was the last problem. So if you have any doubt, you can ask. Hello.
Sir, yes, sir. A small doubt on the fourth problem that you did, sir.
Okay. Here.
Sir, in this one, we solved that only A is a vector space.
Yes.
But the answer is given as B.
Yeah. For the B also you can check. It will be form a vector space. In similar
Okay,
way.
okay, sir.
In similar way you can check.
Okay, sir.
Hello.
Yes, sir. No other doubt.
Okay. If you have no doubt, so you can close the session. Hello. Okay.